Welcome back. Last couple of lectures, we saw something really fundamental, that is how to show Lyapunov stability, and we have seen examples in terms of how one can show Lyapunov stability. But then there is the two conditions, if you recall. Basically, the first condition, V dot, the so-called proxy for the derivative of Lyapunov function, if it is less than or equal to 0, then we know that it is going to be Lyapunov stable. And if it is strictly less than 0, then we'll get asymptotic stability. Now, in practice, we will see that finding strictly less than 0 derivative is going to be very difficult, and therefore we need extensions of this. This particular lecture is basically essentially going to talk about how to show asymptotic stability without necessarily requiring V dot strictly less than 0, but perhaps V dot less than or equal to 0. But the theorem itself is much more powerful than showing asymptotic stability, and therefore we will spend a good amount of time in terms of understanding the subtleties of this particular theorem. Right? So the outline is going to go through this main theorem. It's loosely called by the name LaSalle's theorem, but the original contributions, they've been doing it in a span of 1 year together, sometimes separate, and the technically correct way of calling it as LaSalle's theorem. Anyway, so let's recall our Lyapunov function theorem. There's nothing new there. We want a function to be LFC, Lyapunov function candidate, which simply means it's positive non-zero x and then 0 0. And then of course the second condition is basically this V dot, which we know is V prime of x times f of x, has to be less than or equal to 0, then we can show that zero solution is zero state. When if you recall, basically, if in addition V dot is strictly less than 0, then the zero solution is asymptotically stable. So that is what we know. Okay, and then we want to essentially avoid this V dot strictly less than 0. Can we do something about it? But if you recall, in the lecture on dynamical behavior of systems, we had this wonderful, really fundamental result that says, if you have a solution that is uniformly bounded, uniformly with respect to the initial condition and time, then the positive limit set, the limit points, is going to be non-empty. That means, first of all, this limit point is going to exist. It's not just empty, and it's going to be compact, invariant, and connected. So, and this is going to help us quite a bit. We are going to basically essentially ignore the condition V dot less than 0, but we will look for these invariant sets somehow using this V dot less than or equal to 0. So, before I actually start off the actual formal statement of the result, I want us to understand. So we do have V, which is positive definite. Okay, and then of course we have V of x less than 0, and less than or equal to 0, and this implies Lyapunov stability. Okay, we want to avoid using V dot strictly less than 0. That means maybe there are functions where we cannot find that, but yet we can achieve asymptotic stability. That's the point we're trying to make. So how can we show asymptotic stability using this function that has this V dot less than or equal to 0? If we had a strict less than 0, then we would get it automatically. Asymptotic stability, we proved that earlier. But if we had only less than or equal to 0, what can we say? Well, one of the observations that we can see is V of S of t comma x0, so that is V evaluated on the path, is decreasing, non-increasing. That's the correct way of saying it. So it's always going same or down. So one of the nice things about such functions, as a function of time, this is going to be monotonically, monotonic. That means it's either going to remain same or decreasing, right? So one of the nice things is basically limit of such functions exist. Okay, and let's call that C. Because V is a non-negative function, V of 0 is 0 and then V of x is positive, so C could be either 0 or positive. So this is clearly we seek to right? What else do we know? Since limit of t tends to infinity is going to be C, right? All the limit points of the solution S, which we call as limit set, is going to be part of this set. So one of the things that we can conclude therefore is omega of x0 is going to be subset of this set x given by v of x is equal to C. I don't know what this C is. All I know is some non-negative number. But omega is going to be subset of some set like this, right? And such sets we call them as level sets, okay? Of B, of course. Earlier we saw when we have less than equal to C, we call them as sub-level sets, and this one is called a level set. So what can we say about these level sets? Level sets are not necessarily invariant, because once we start there, it's possible that we can escape. One of the points B dot may be strictly less than 0 and we can escape. But the fact that omega x0, wherever we started, we have the limit set. Omega x0 is invariant. So we know that this is invariant. Okay. So that means if I start in that set, then I'm going to remain in that set. Okay, which means because it's a subset of that, I can find. So if I'm going to use some other notation. Y0 belongs to my omega of x0, right? This is a notation like made in some sense. Omega of x0 is the limit set of some arbitrary initial condition we chose. The trajectory eventually supposed to reach or not enter finite time, but for the conditions we typically assume. But omega of x0 basically is the set of limit points of our original trajectory. Now I'm going to start off an imaginary exercise where I'm going to pick one of the points. We know that it's going to be non-empty because this entire thing is bounded. How do I know this is bounded? V of 0 is some number, and then V is always decreasing, so V is a positive function. So essentially this entire trajectory is going to be bounded. So this omega x0 is non-empty, compact, invariant, and connected. We know that from our theorem. So if I'm going to start off in one of those initial conditions, then what can I say? Because it's invariant, S of t comma y0 is omega of x0 belongs to x0 for all t in R, right? I mean, t greater than 0 for sure, but t belongs to R because we know that much more than just positive invariance being invariance, right? So what does this mean? Well, this simply means v of s of t comma y0 is going to be equal to constant. So by taking derivative, v of s of t comma y0 is going to be 0. Okay. So we can actually just focus therefore on v prime of f of x is equal to 0, right? And then in some sense start looking for invariant sets in that, and those invariant sets will provide us where we want to go, right? So in other words, basically what we are saying is s of t comma x0, okay, this is the original trajectory, okay, no longer in this invariant set, the limit set, will go to some m where m is the largest invariant set in the set v prime of f of x is equal to 0, right? So what do we mean by largest in terms of inclusion? So basically, if we have two sets, the union of the two sets is going to be bigger than each one of them. That's the logic we use. So when I say largest, basically pick all the union of invariant sets within this. So essentially, the LaSalle invariant theorem will say this formally, right? So we're going to consider this ODE x dot equal to x, and the theorem is slightly more general than what I just showed, and we will discuss that in a second. So let DC be some compact positively invariant set, and then V is some function that satisfies this V dot is less than equal to 0. It need not be positive definite, right? And basically pick this set R, which is nothing but set of all x's such that V dot is 0, and M is the largest invariant set in the sense that I said, two sets, the union is bigger than the individual set and things like that. In other words, take the union of all invariant sets within this set R, and the conclusion is if we start within this D sub C, then x of t is going to go to n as t tends to infinity. Hopefully you understand that x of t going to a particular set simply means that basically as t tends to infinity, it will get closer and closer to at least one of the points or multiple points, right? It's possible that the trajectory is going to go around that particular set, and then therefore it may be close to a bunch of points. In other words, at least there is one point in M that is getting closer and closer as t is close to infinity. Basically, the distance between one of the points and this particular x is going to be very close to 0. Right? So let's get back to this. Why do we need this assumption D sub C compact positively invariant set? If you recall in the discussion earlier, I said basically we can use positive definition to show that this solution is going to be bounded and so on and so forth. Instead of that, we will use this more generic assumption that we have to start with somebody gave this positively invariant set, right? We need not calculate or estimate this from some positive differential function. So in that sense, we need not be anything, right? But it's going to be lower and upper bounded because D sub C is a compact set. So there's a wonderful analysis result that says that if you have a continuous function, that's something that I didn't put, but V dot is possible only if it's continuously differentiable. So if you have a continuous function on a compact set, then you'll have minimum and maximum. So in that sense, V is lower and upper bounded. So all those things are generic enough. They need not be positive. That's the point that LaSalle, Babashan, and Krasowski made. So this is far more general in that sense. We need not have anything to do with stability. It can actually be used to show even Lagrange stability, which, if you remember, just the boundedness of solutions, right? Because it may sound silly. Basically, we assume that it is bounded, and showing bounded is silly, but you can show asymptotic behavior that is bounded. We can identify the specific limit sets where these solutions are applicable, right? So in that sense, this is a very general convergence result. Stability will not come for free in the way that we stated. We need to state that separately, right? So we saw the proof of it. Basically, essentially, some V is there, and then V dot is less than or equal to 0, and then since it is lower bounded, basically V is going to converge to some number C, and then on that set, we're going to basically conclude that the limit set is going to be there, and then on the limit set, V dot is going to be 0. So we're going to look at the largest invariant set. This becomes an algorithm for finding out these omega limit sets. And when we see examples, then we understand a lot of these things quite well, right? So perhaps that's what we will do next. So if we have this standard system, this happens to be a Lyapunov function candidate, but we're not interested in that. We are interested in limit sets. So if I'm going to compute V dot, I'm going to get x1 times x1 dot plus x2 times x2 dot, which is going to be equal to x1 x2 minus x1 x2 minus x2 squared, right? So this and this cancels. We will get V dot is equal to minus x2 squared, which we know is less than or equal to 0, but it's not strictly less than 0, because for any value of x1, this can become 0. So it's not strictly less than. So we cannot conclude asymptotic stability, right? Though that's not the goal in this particular example, but we will conclude. So what can we say? Well, remember we have to construct this set. I mean, when we apply the Barbichan-Krasowski theorem for this particular example, where do we get DC from? Well, we can basically pick the set V of x less than or equal to V0, and then that becomes your DC, and you can clearly see, since V dot is less than or equal to 0, this is going to be an invariant set, positively invariant set. It's bounded because of the nature of V of x. It happens to be a quadratic function. So all those nice things will be there to show that D sub C is indeed positively invariant set, defined as such, right? So that is a lesson in some sense. In many ways, finding that DC is going to rely again on some kind of positive definiteness of the upper function. You can have less general than positive definiteness, but we have to do that exercise of finding the D sub C. In this case, we get it through the positive definiteness of V. Right? So moving forward, so we have this D sub C, and then we have to look for x such that V prime of x, f of x, is equal to 0. But that is nothing but minus x2 square. So this is all x1, x2 such that x2 is equal to 0. Okay. So on the real line, basically, it's the horizontal line. The x-axis is going to be the r, right? So now, what is our job? On the real axis, right? We have an invariant set, and we have to identify that, right? So, since it is invariant, basically, if we start on that invariant set, x of t is going to initially be 0, and it will remain 0. So x2 dot is also going to be 0, x2 is going to be 0, right? On that set, we will therefore get x1 dot is equal to 0, because x1 dot is x2 happens to be 0. But x2 dot is also 0, so x2 dot, and then we get x1 is also 0, right? I mean, I was going to say x1 dot is 0, so x1 is constant, but the second equation tells you x1 is equal to 0, right? So please understand, these arguments are quite subtle. If you look at this equation, right, we know on the set R, x2 is 0, right? In that set R, we are looking for an invariant set. And the nice thing about invariance is basically, if something is true about that particular set, it will remain to be true throughout, right? So because this invariant set is entirely containing R, if I'm going to start at 0 with x2 is equal to 0, I'm going to remain at 0. So in that sense, x2 is going to be 0 for all the time. So therefore, we can conclude on that invariant set x1 dot is 0, right? Then we will come to the second equation that says, I know that x2 is 0. But x2 is 0 also implies x2 dot is 0. So therefore, x1 is 0, right? So if x1 is 0, then basically x1 dot is going to be 0 free. So it's an additional information that we get. So x1 is 0. So what does this tell me? 0, 0 is the only invariant set in R. Okay. So that means our omega of x0 is basically is equal to this. So what does this mean? Every point wherever I am, I'm going to go into 0 as t tends to infinity. And that, of course, we have Lyapunov stability from the fact that v dot is less than or equal to 0, and we have convergence. Both combined together, we can conclude that this zero solution is indeed asymptotically stable. Right? So this is a cool way of showing asymptotic stability. Okay, without ever requiring v dot strictly less than 0. And let's not underestimate the power of this particular result, because many a time we end up using this result to show asymptotic stability. It's very difficult to find functions that are both Lyapunov function candidates, that means positive definiteness, and strictly less than 0. Even not as v dot less than or equal to 0, it's not easy. But when we do find v dot less than or equal to 0, we can use this trick of LaSalle's invariance theorem to show much more than simply Lyapunov stability. Right? So we will summarize this. Basically, if you have x dot of f and DCB compact invariant set, and B is in this particular case LFC, V dot is less than or equal to 0, then the conclusion is if R is given by this and then 0 is the only invariant set, right, then 0 is asymptotically stable. One of the things that I forgot to mention is basically f of 0 is going to be 0. Otherwise, we cannot even conclude any of these things. But with that additional assumption, basically, what we conclude is asymptotic stability. In reality, DC being compact invariant set is not necessary because this LFC is going to give you, but this LFC could be very local. Therefore, we can actually conclude some of the things much more than the standard LFC function result. But in all these, we can actually conclude if all these conditions are satisfied, then DC is actually going to be region of interaction, right? So what did we do here? Like in the previous example, we showed that the only invariant set in R is going to be 0, and by ensuring that our system is 0 is Lyapunov stable through a Lyapunov function, then we can conclude all these things. Right? Now, at times in practice, one can actually use one function for showing Lyapunov stability and a completely different function, which need not be a Lyapunov function candidate, but we can use the basic Lyapunov theorem to show 0 is the only convergent point, and combine convergence and stability, we can get basically conclusion that this 0 is asymptotically stable. So in that sense, understanding the result is very, very important. It's quite subtle, and you'll see in a few examples. Yeah, so let's see. Let's go to example 2. So here I'm going to have this example that we considered earlier to show Lyapunov stability, and we will pick this Lyapunov function happens to be Lyapunov function because this is v of 0, 0 is 0, and v of x is indeed greater than 0, x 0, closely to this particular thing, right? And then I'm not going to show the details. We can show that, well, let me show it. So theta double dot minus plus theta dot sine theta, and theta dot times theta double dot, I'm going to get minus theta dot square minus theta dot sine theta plus theta dot sine theta, and we can cancel these two, giving us minus theta dot square, and which we know is less than equal to 0. So 0 is Lyapunov stable, right? Now, what can we say about your LaSalle's theorem applied to this, and then can we show that converges to 0, 0? Well, your standard thing is basically theta dot is equal to 0, so which is basically all the points on theta dot plane such that theta dot is 0, right? Once again, using the logic that this will have, we are trying to find the largest invariant set in this set, and if it is invariant, then we know that theta dot is going to be identically 0, right, wherever you start. So therefore, theta double dot is going to be identically 0. So which means sine of theta of t is going to be equal to identically 0. So and that means theta is going to be an equilibrium point, right? So you know, all the equilibrium points could be your answer, right? Now, but of course, in this particular case, we showed positive definiteness only close to the 0 equilibrium point, so we can only conclude Lyapunov stability. And so, what this simply means basically, you know, the d sub c that we need in the LaSalle's theorem is coming from this positive definiteness, and then that's only around the 0. So the 0, 0 equilibrium point is shown to be asymptotically stable, right? But something like pi comma 0, I'm going to leave it as a question mark for the time being. So let me repeat the argument here. So we have this v of 0 comma 0 is equal to 0, and positive definiteness. So we can find some level sub-level set which is positively invariant set, right? Positively invariant. And that's the starting point of our LaSalle. And then we showed that V dot is less than or equal to 0. And using this set R, we look for an invariant set in that. And when we look at the invariant set using the dynamics, we can show basically theta dot is identically 0. That's coming from your basic condition. And theta double dot is therefore going to be identically 0. Theta dot is 0. Theta double dot is going to be 0, which implies that from the original dynamics equation, sine of theta is equal to 0. So, which means basically all the equilibrium points. If at all R contains all the equilibrium points, then we will get. Yeah, so let's summarize this entire thing. So we have this positive definite function, and which we can use to show that there is a positive invariant set, so that you get this bounded solutions. And then V dot is less than or equal to 0. Then we look for this invariant set theorem application, and then we can show that 0, 0 is asymptotically stable. But of course, there are other equilibrium points that we can get from this set argument, but we cannot show really much about it. And then I'm going to leave it as question mark for the time being, right? So, how do we show global convergence? Well, I mean, it's relatively straightforward. We want all these nice things to be true globally. And the general result is basically, you have this set M, which is part of this R, and we'll get global convergence, right? But it doesn't show anything about asymptotic stability or anything like that. It's simply global convergence. We will have, if at all f of 0 is 0, then we can conclude Lyapunov stability, but not beyond that, right? So if you want global asymptotic stability, then we will have to conclude that we need additional condition that V of x goes to infinity as x goes to infinity, and 0 is the only invariant set in this thing. Right? So then 0 is globally asymptotic. Right? So in the previous version, where we don't really require any of these things, we can only use it for showing how this whole thing is going to converge to some set, right? If we have some D sub C that is invariant and things like that. Whereas here, on the other hand, we actually will require this radial unboundedness condition, which is V of x going to infinity as norm of x goes to infinity. And also this set R will have only one invariant set, and therefore we can conclude 0 is globally asymptotic, right? So this is a very powerful result. Essentially can avoid V dot requiring to be strictly negative to show global asymptotic stability or exponential stability of the neutros. But we can use it much more. In many cases, we can actually use one function to show Lyapunov stability, another function to show global convergence and things like that, right? So there are many interesting extensions to these results, both on the Lyapunov side as well as LaSalle's theorem side. For example, the extensions to time-varying systems, discrete time systems, periodic systems can be found in the references that I provided before, by Darwin Chalaboina or Vidyasagar's book, Classic by Vidyasagar. And we can actually see a very general discussion of Lyapunov function theorem and LaSalle's theorem, and easily applicable to infinite dimensional systems, the resolutions to PDEs and whatnot, especially when we're dealing with, say, even time delays in ordinary differential equation. The infinite dimensional systems concepts have to be dealt with. So all such concepts are very clearly discussed in this book by Zia. And there are associated theorems related to periodic systems, and one celebrated theorem is Poincaré's theorem, which seems like a one-off result that is on stability, but it's somewhat excuse my typos here, but Poincaré theorem is one of those theorems that talk about stability of some periodic orbit by looking at an interesting mapping of this periodic orbit, particular plane and things like that. And it actually shows rigorously that the system, the periodic orbit, is going to be stable, right? So it seems that's a stability result that doesn't depend on Lyapunov functions. So the question then, therefore, can we actually also bring that into Lyapunov function? And that you can find in this paper titled Lyapunov function proof of Invariance Theorem. And of course, we assumed everywhere that V is the Lyapunov function is continuous and differentiable and things like that. But there are advantages for actually assuming a little bit discontinuity, specific discontinuity, lower semi-continuity, and such concepts have been explored in this particular paper and actually related to this. And then finally, we have a whole set of trajectories that are not necessarily continuous. I'm not just talking about discrete time versions, but actually continuous trajectories with discontinuities in the trajectory. And such things come from hybrid systems or impulsive systems. And there is a very general theorem that we showed a while ago, invariance principle for such systems which have these discontinuous trajectories. So we have to assume certain features of discontinuity. It's not arbitrarily discontinuous, but nevertheless we can actually show something quite interesting for such discontinuous trajectories. So the summary of last few lectures is basically Lyapunov functions provide a way to show stability of equilibrium. And then you have this completely independent result by LaSalle's, which shows basically how to show convergence to some sets, right? And once we have combined both these things, we'll have actually we'll have the most powerful way of showing asymptotic stability. Right? So in many results that we see in the class, we will keep using definitely the standard Lyapunov function result, but many times we rely on the version that LaSalle's gave us. Right? In addition to this concept, this is a concept on semi-stability that you can find in the paper by Bernstein. It's a wonderful concept. It's one of those concepts that I don't choose to discuss in this particular thing, but it is inherently connected to, again, convergence of these results, right? Convergence of these trajectories. Right? So in the next class, we will actually look at converse versions of Lyapunov stability, right? Functions rather. So so far we have seen that if we find a Lyapunov function, we have a sufficient condition to show that systems, the zero solutions are stable. Now, do we always have a Lyapunov function? That's a standard question to ask, right? Because we keep mentioning that finding Lyapunov functions is difficult, right? So can we always find Lyapunov functions? So that is covered in the converse theorems. And then, of course, the nice thing is if we cannot show stability, can we show instability, right? And those will be covered in the instability theorems. Right? And after that, we'll go through a tutorial mode and consider a bunch of examples and use these two theorems at our will, and then show many examples in which how to find these functions. I mean, how to find is a little bit difficult, but at least by guessing something, and then we will show all the conditions to satisfy, and the subtle usage of this invariance theorem and things like that we will see and can conclude stability various solutions. Thank you.